Welcome to Lecture 2 of Machine Learning for Mathematicians. Today we do tensors properly as multilinear algebra meeting memory layout. We also settle the question I left open last time, which is why the mathematics writes a matrix acting on a column while the library writes a product with a transpose. The reading is Dijksenroth, Feisal, and Ong, together with Prince's appendix on mathematics. Let me start by separating two things that share a name. In your training, a tensor is a multilinear map on a vector space and its dual, and it carries a transformation law saying how its components change under a change of basis. That law is the whole content of the definition. In this field, a tensor is an n-dimensional array with a shape, a data type, and a memory layout. There is no transformation law and no distinction between upper and lower indices. These are not the same object, and pretending that they are wastes about a month. What does survive intact is the part you actually use every day. Outer products, contraction over a repeated index, the summation convention. So keep the index bookkeeping and drop the transformation law. Everything in this lecture is either a fact about the multilinear map or a fact about where the numbers sit in memory, and those two get confused constantly. Because they get confused, we are going to label them. I will call a statement a map claim when it is about the function being computed, so it would still be true written out on paper. I will call it a layout claim when it is about bytes, strides, and caches, so it would be false on a machine that stored things differently. Here is the ledger for today. That index notation is orientation-free is a map claim. That broadcasting is an outer product followed by a pointwise operation is a map claim. That the transpose costs nothing is a layout claim. That the weight is stored with outputs first is a layout claim. That reshape sometimes copies is a layout claim. And here is the payoff. The famous conflict between writing a matrix times a column vector and computing a batch times a transposed weight is entirely a layout claim. Lecture 1 promised this lecture would settle it, and the middle of today does exactly that. First, the only type this system has, which is shape and what it does and does not catch for you. A tensor's shape is a tuple of sizes, and its rank is the length of that tuple. Now here is the thing worth internalizing. That tuple is the only compile time information in the entire system. There is no type checker downstream of it. So a shape that checks out is a program that runs, and running is not the same as correct. I'm going to fix a notation now and use it on every frame for the rest of the course. A lowercase bold letter is one sample. A capital letter is a batch of them. A weight has outputs first and inputs second. Every frame from here that carries a tensor expression gets a shape line underneath it. Write that shape line before the expression, not after. 9 confusions out of 10 are an axis, and an axis is visible in the shape line and completely invisible in the formula. Now, contraction, sum over a repeated index. That single move is the matrix product, the inner product, the convolution, and the score matrix inside attention. In the summation convention, you write it by repeating a letter, and the striking thing is that the code says the same thing in the same letters. The mathematics reads y sub I equals w sub I jx sub j plus b sub I. Directly beneath it, the code reads in sum of the string I j comma b j gives b I. The subscript string is the formula. Indices before the arrow name the operands. Indices after the arrow survive into the output. Any index that appears before the arrow and not after it is summed over. So the summation convention is your first language here, not a concession to programmers. An in-sum string is index notation with the summation signs deleted, which is exactly what Einstein deleted. There is a second habit worth forming, which is that every tensor operation factors into 2 steps. The first step is the outer product, which adds the ranks. The outer product of u and v has components u sub I times v sub j. The second step is contraction, which removes 2 indices by summing a repeated one. A matrix product is one of each. You form the outer product of w with x, which has 3 free indices, and then you contract 2 of them. No library ever builds that intermediate object, and note carefully that this is a layout fact rather than a map fact. The map really is the composition. So when you meet an unfamiliar tensor expression, read it as outer product first, then contract. The shape of the answer follows without any thought at all, and the shape of the answer is the thing you keep getting wrong. Next, broadcasting, which looks like a convenience feature and is actually a piece of multilinear algebra. Here is the rule, stated once. Align the two shapes from the right. In each position, the two sizes must either be equal or one of them must be 1. The result takes the larger of the two. A missing leading axis counts as 1. That is the entire rule. Look at what it gives you. A column of 3 against a vector of 4 produces a 3 by 4 array. A rank 3 shape against another rank 3 shape works whenever every position matches or is 1. A batch of samples against a single bias vector works, and that is why adding the bias works at all without you doing anything. And a 3 by 4 against a 4 by 3 is rejected, because 4 meets 3 and neither of them is 1. That last row is worth dwelling on, because it is the only case in this whole business that the machine will catch for you. Now, why it is not a convenience feature? Take U in 3-dimensional space and V in 4-dimensional space. Broadcasting U against V pulls both of them back along the two projections out of the product space, and then applies the operation pointwise on that product. For multiplication, that composite is literally the outer product, with components U sub I times V sub j. The verification confirms all three parts. The broadcast product of a column of 3 and a vector of 4 equals the outer product exactly. The rank 3 example gives the shape the rule predicts. The mismatched pair is rejected. So broadcasting is a pullback along projections. Once you see it that way, the rule stops needing memorization, because aligning from the right is just a statement about which factors the product is being taken over. Broadcasting is also free, and it is worth seeing why. When an array is expanded, the result is a view whose stride along the broadcast axis is 0. A stride of 0 means the reader advances along that axis without advancing in memory at all. So the same element is read again and again while being stored exactly once. Its materialized twin is a genuine allocation. The measurement makes the difference concrete. The expanded view shares storage with the original and holds 16 kilobytes. The materialized copy does not share storage and holds 67 megabytes, which is 4,096 times as many numbers for the same map. So a stride of 0 is the whole trick, and notice that this is a layout claim. The function being computed is identical either way. Only the memory differs, and it differs by 4 orders of magnitude. And now the bug that the rule cannot catch. A stray trailing axis of size 1 is legal everywhere, so it never raises anything. Watch what happens. The predictions have shape 5. The targets have shape 5 by 1, because something upstream kept a column. Their difference is not rejected. It quietly becomes a 5 by 5 matrix of all pairs, and the mean of its squares is a perfectly good number. The intended error and the one the stray axis computes differ by a factor of about 1 2/3. The wrong loss is finite, it is differentiable, and it decreases. A model trained against it converges to the wrong thing, and nothing anywhere reports a problem. So shape is a type, and this is the type system's blind spot. An axis of size 1 is compatible with everything, which is exactly what makes it dangerous. Squeeze early, and print your shapes when a loss looks strange. Now the question I promised to settle, about columns, storage, and where the transpose comes from. Let me state the conflict fairly before resolving it. Every book you have read and every slide in this course writes y equals wx plus b with x a column vector. Every framework instead computes a batch matrix times a transposed weight, with the samples in rows and a transpose that no textbook ever mentions. 3 explanations circulate for this, and only one of them is right. The first says the field uses row vectors. That is false, and the mathematics is entirely unchanged. The second says the transpose is there because it costs a copy and somebody optimized it away. That is also false, and the next frame measures it. The third says it is a memory layout decision, and that one is true. So the disagreement was never about mathematics. It is about which axis runs fastest in memory. Index notation has no opinion on that question, which is precisely why this course crosses the boundary in indices. So let us measure it. A tensor is 3 things: a pointer into a buffer, a shape, and a tuple of strides, giving the step and elements along each axis. Transposing swaps two entries of the shape and the same two entries of the strides. It does not touch the data at all. Here is the run. The weight has shape 128 by 256 with strides 256 and 1, and it is contiguous. Its transpose has the shape reversed and the strides reversed, and it is not contiguous. And the data pointers are identical, so nothing was allocated and nothing was moved. The cost of that transpose is the cost of writing down two integers in a different order. So the transpose in the library's expression is not a performance concession, and it is not a mathematical statement. Lecture 1 promised this, and here it is. That leaves the real question, which is why the weight is stored with outputs first. The contraction sums over the input index. A cache wants both operands to run along that summed index contiguously so that each of the two streams is read in order rather than jumping. Storing the weight with outputs first achieves exactly that. The run confirms both halves. Row I of the weight, which is output i's weight vector, has length 256 and is contiguous. Row k of the batch, which is sample k's feature vector, has the same length and is also contiguous. Both sides of the sum run along the fastest axis. And the transpose in the library's expression exists so that the result comes out with the batch index still leading. So the storage order is the shape the mathematics already uses, chosen so that both sides of the sum are contiguous. That is a statement about caches and about nothing else. Here is the verification frame, and it has a surprise in it. 4 lines, the library's own linear layer, the column form applied one sample at a time, the idiomatic batched form, and the idiom sum form. Against the library, the idiomatic form and the in and sum form agree exactly to the last bit, and so do their gradients. The column form does not. It differs by about 8 in 10 to the 14th. That is not a bug, and it is worth understanding why. The rounding floor here is the unit round-off times the size of the answer, which comes to about 1.5 in 10 to the 14th. So the discrepancy is about 5.5 of those units. A matrix times a vector and a matrix times a matrix are different library kernels, and they sum the same 256 products in a different order. Addition in floating point is not associative. Same map, same mathematics, different last bits, and lecture 10 is entirely about that. Finally, contiguity and the operation that will refuse to run rather than pay for you. An array is called contiguous when its strides are the row major ones, meaning the last axis has stride 1 and every earlier stride is the product of all the sizes to its right. So a 4x6 array has strides 6 and 1. Transposing it gives strides 1 and 6, which is not of that form, so the transposed array is a perfectly good tensor that is not contiguous. Contiguity matters for exactly 2 reasons. First, some kernels require it and will silently copy to get it. Second, an operation that must reinterpret the raw buffer rather than merely reindex it cannot be done on a non-contiguous array at all, and that one is the next frame. So not contiguous is not the same as not usable. It means the elements sit in the buffer in an order other than the one the shape suggests, and the strides are what reconcile the two. Which brings us to the difference between view and reshape, and it is a real one. View promises never to copy. That promise forces it to refuse whenever the flattened order you asked for is not the order actually in the buffer. Reshape makes no such promise, so in the same situation it copies instead, and it does not tell you. The run shows both. The original array is contiguous, its transpose is not. Asking the transpose for a view raises an error, saying the requested size is not compatible with the tensor's size and stride. Asking it for a reshape succeeds, and the result does not share storage, which means a copy happened. Asking the original for the same reshape succeeds and does share storage, so that one was free. So view raising is information, not an obstacle. It is telling you the flattening you asked for is not free. Reach for view first and let it complain. Now, what does einsum actually cost? There is folklore that it is 2 or 3 times slower, so we measured it. The table sweeps the same contraction written 2 ways across 5 problem sizes. The last column is a control. It times the idiomatic form against itself, so it tells you the smallest difference this machine can resolve at all. Read the gap column down. It sits near 12 microseconds, at the smallest size and near 35 at the largest, while the work being done grows by a factor of over 4 million. On the last row, the gap is smaller than the control, which means it was not resolved. So the ratio falls from nearly 4 to about 1. Einsum is not a slower algorithm. It lowers to the same library call and adds a fixed charge for parsing the subscript string and planning the contraction. A fixed charge amortizes. Hence the rule for this course, einsum to teach and to verify, idiomatic in the inner loop. One more measurement, and it is the one that motivates the rest of the course. Consider two transpose bugs. In the first, you transpose the wrong operand. The shapes disagree, the library refuses to multiply them and says so by name, and the cost of that bug is nothing at all. In the second, you transpose a square weight. Every shape still agrees because it is square. So the program runs, it trains, and it computes a different function. The two answers differ by about 99, which is enormous, and nothing anywhere raises. So shape checking is free, and it catches a great deal, which is precisely why it lulls people. Whenever the shapes cannot distinguish two candidate expressions, only a number can, and producing that number is what every remaining lecture in this course does. Let me leave you with the rules this lecture fixes for the rest of the course. Columns in the mathematics, always, because it matches every book, and because the row form was never a mathematical claim in the first place. Index notation at the boundary with code, because it has no opinion about orientation, and because it is in sum verbatim. A shape line on every frame carrying a tensor expression, because 9 confusions out of 10 are an axis. Einsum to teach and to verify. Idiomatic to train, because the measured cost is a fixed charge per call and not a multiplier. And label every claim as a map claim or a layout claim, because almost every argument you will read in this area is two people answering different questions. The transpose question is now closed. It will not appear again except as a worked example, and any later lecture that seems to reopen it is making a layout claim. 5 things to keep from today. First, the multilinear algebra survives and the transformation law does not. What you keep is the outer product, contraction, and the summation convention. That convention is an einsum string with the summation signs deleted. Second, broadcasting is a pullback along projections. For multiplication, it is literally the outer product. It costs nothing because the broadcast axis carries a stride of 0. Materializing it turned 16 kilobytes into 67 megabytes. Third, a straight axis of size 1 broadcast silently. It produced a loss wrong by a factor of about 1 2/3 with no error anywhere. Fourth, the transpose shares storage with the original, so it is free. The weight is stored with outputs first, so that both sides of the sum over the input index are contiguous. All 3 spellings of the affine map agree. 2 match to the last bit, and the third to about 5 units of rounding error, and their gradients agree exactly. Fifth, einsum costs a fixed charge of roughly 20 microseconds per call rather than a multiplier. At the largest size we tested, that charge was below what the machine could measure. Next time we translate a paper into code, symbol by symbol,